Greetings, ladies and gentlemen. I am the great Mokiki, and I am about to grace you with the greatest performance of your life. Follow me. For my first trick, I will need a card and a coin and my attractive nature. It is called Mokiki's hundreds. Anyways, so I put the card and then the coin, and as soon as I pull it, habby-dabby. How does she do it? You will never know. A magician never reveals her secret.
That's not magic, that's physics.
Well,
it happened because of Newton's first law. See, Newton's first law states that an object will remain at rest or in constant motion if another force is not acted upon it. Newton calls this an object's inertia, which is basically the object's desire to stay at rest or in constant motion. This law applies to the penny. Since the card moved so fast under the coin, it had no time to react to the card's movement, allowing for the penny's inertia to keep it in place, making it land on your finger. If you were to move the card any slower, the penny would have went with it. It's simple physics.
How dare you question me? Get out!
Fine.
Now that my distraction has disappeared, I shall show you my final and last trick, which is called Mokiki's seesaw. All I need is a long double-sided candle, 2 glasses the same size, and a souvlaki stick to be pierced at the midpoint. I will now light both ends, and the candle will begin to totter. As you see, one end is heavier than the other, but soon the candles will begin to totter and reach a point where I make them stop at an equilibrium.
Why?
Augusta, we have it. I am the great Mokiki.
Stop! You're insane if you believe that you're the reason for all this. The whole reason why the candle moves is because of Newton's third law. Newton's third law states that for every action, there is an opposite and equal reaction. It can be applied with the wax. Each little drop of wax that falls off the candle creates a force upwards on the candle, helping it move upwards. In addition to the force, the mass also decreases, making the other side heavier and causing that side to fall. This process is repeated on the other side. On that end that points downwards, the wax falls off easier as it is closer to the flame, resulting in a lower mass. As the end pointing up becomes heavier than the other end, gravity pulls it until the lighter end is now upwards. If one side of the candle starts out heavier than the other, the motion of the candle will act to equalize the mass on either side. This is due to the natural momentum of a mechanism. Momentum is quantity of a moving object and is always conserved in a system. If momentum is conserved and the mass decreases, the velocity must increase. The loss of mass increases the velocity of its motion. If the mass of the candle on both sides is equal, the candle will stop moving because the system will be at equilibrium. That's basically your whole trick.
You are a great fool to believe in this great god called Newton. But I'm beginning to understand this schmoop that is coming from your lips.
Thanks.
Please, tell me more about this. Wrap it up, Stephen. Let us go. More Newton.